All right, let's do it. So, can we get the lights on? All right, you can see here, here's the link to this set of slides. If you follow this link, it'll take you to a folder that contains the slides for all days. All right. So, reminder from last week. We've defined these functors EA and FA for every element of FE. And what we showed is those give you kind of two interesting pieces of structure on symmetric groups of characteristic P. One is they act on the Grothendieck group. They act on the Grothendieck group by giving you a representation of SLP hat. It's a particular. So if you know about SLP hat, that can tell you some interesting stuff about representation theory. I understand that you guys, many of you don't know it as well, so I won't worry too much about that. The other thing they do is they act, and remember the way they act is you've done a simple with the functor, and it has a unique simple quotient and a unique simple sub, which are the same. So it acts on these simples by Categorical operators and give you a copy of the crystal graph of this theorem. But the representations of KSN aren't just like a lump of things. They have a structure, and the structure is the structure of this graph. So here's a P=2 example of this. I've drawn this in a way that sort of brings out the SL2 hat structure a bit more. So I've consistently shown F0 is going down this way, and F1 is going down this way. So where you are on the board is your weight in terms of the module over SL2, because the way you figure out that weight is F0 and F1 change in a consistent way. All right, so today what I want to talk about is another application of these functors is Chuang-Rouquier equivalences. And these tell you about the relationship between different blocks of KSN for different values of N. So I'll just remind you what these blocks are. So let me just say the words. Blocks means the simples that can appear as composition factors of an indecomposable module. So this is kind of the blocks are the finest way of breaking your category up into subcategories that don't have any extensions with each other. For the symmetric group, there's a very nice answer for when two ERFs lie in the same block. So I prefer this way of saying it. If they have the same number of boxes of a given content mod P for all elements of Z mod P. So one reason I like this is it makes it clear two things are in the same block if their classes in the Grothendieck group are weight vectors of the same weight. This number of boxes tells me the weight. And so that's an equivalent way of rephrasing this. You'll more often hear this explained by modular representation theorists by saying that two things are in the same block if after you pull off the same number of P hooks, you end up at the same P core. So P hook, again, hopefully heard this at some point, is a rim hook that has P boxes. So it's P consecutive boxes off the outside of the diagram. You'll note you have to get boxes of all residues in FP exactly once in a P hook. So moving a P hook, all it does is it decreases these numbers Pi by 1 for all I. And a P core is a partition with no removable P hooks. So it's one where this process terminates. And the number of P hooks you pull off has this incredibly unfortunate name. It's called the weight. And this was just a very bad choice because it doesn't correspond to the weight as a representation of SLP hat. That's just how life is. I tried consistently to say P weight to mean the number of P hooks you can pull off. All right, so just to kind of give you a feel for these definitions, here's the crystal graph with P equals 2. The things I've circled in green are the two cores. They're the partitions where I cannot pull off two consecutive boxes from the outside of the partition. Right here, there's just no way to do it, right? I try to get two consecutive boxes, and there's always a box that they're stuck behind. Actually, the two cores are just always the staircases, but in general, this is a bit more complicated. This is an example of a P-regular partition, such that when I pull off a 2-hook, the whole thing is a 2-hook, so I get the empty set. Here, if I pull off a 2-hook, I get a single box. Here, if I pull off a 2-hook, I get this 3-box staircase. And then these purple guys are ones where I can pull off two 2-hooks. Actually, all of these I can just pull off a ribbon of length 4. And again, this guy goes to the empty set, this guy goes up here. So P equals 2 is particularly nice. Everything flows out into these diagonals. And of course, I've drawn this exactly so that removing a box of content 0 and a box of content 1, which is what happens if you remove a 2-hook, just brings me straight upwards. And if you're used to the representation theory of sl2 hat, you should also see the Weil polytope here. Difference between these guys are all positive roots for sl2 hat. All right.
For the columns of the blocks?
No. The columns tell you what 2-core you're on, but it's also how many hooks you have to pull off for the 2-core. So the block corresponds to your like location in the plane. Of course, these guys I couldn't put in exactly the same place, but right, because I go down to this slope if I add a box with label 0, this slope if I add a box with label 1, because those directions are linearly independent. If I'm in kind of two different positions on the plane, I either have a different number of boxes with label 0 or a different number of boxes with label 1. And so I'm not on the same. On this page, there are only 2 examples of 2 regular partitions, which are in the same block. So every circle contains the partitions in one block. Just because 2 is small, as we know, it's the oddest prime. This is the only case where there are positive p-weight blocks with only one symbol. For all the other primes, any positive p-weight block will have multiple symbols. All right. And just to kind of remind you, because I know I went by everything very fast, and unfortunately happened in this case as well, to kind of remind you about this crystal operation, how it works. Here's an example. So this is in characteristic 2. I'm looking at this staircasey guy. That's a simple Speck module. It's 2-dimensional. It's the usual kind of reflection representation. If I induce that up from S3 to S4, I get an 8-dimensional representation. And if I just count boxes, it has to involve these symbols. And if you follow through everything I told you and take into account the dimensions of these, there's only one thing that could possibly happen. So I'm supposed to be getting something that looks like the cohomology of CP2. That's these 3 copies of this guy, which is the Categorical operator for 0, applied to this staircase here. So that's going to be the sub. It's going to be the quotient. The quotient, the sub. And then there's going to be a guy in the middle. And I kind of know it has to have this structure because I have multiplication by the dot, which in this case is just the use of Murphy. And that always behaves on the composition factors for the Categorical operator like multiplication by the hyperplane class in the cohomology of CP2. So it sends this composition factor to this one, and then I do it again, and it goes here. There have to be composition factors of the trivial, sandwich in the middle. It has to send this guy to this guy. And you'll note here, this is kind of one of these illustrations of why do I have a simple sub and a simple quotient and they're the same. If I do this twice, I get a map that has simple image. And that simple image, well, it's a sub and it's a quotient. So there you go. All right. So this is just kind of give you a little bit of a feel for how does this work in general. So you always have a good handle on how the guy that corresponds to the Categorical operator shows up, but it's much less predictable what these other composition factors stuck in the middle are. That's basically why modular representation theory is fun. Right. Any questions about this picture? All right, so if you're used to this kind of general theory of finite groups, the p weight of a block determines what the defect group is. It's going to be a p sl2 of the symmetric group of order w times p. So in particular, the block of p weight w with empty core is the principal block for this symmetric group. And what this defect group measures is kind of how non-semi-simple the block is. And I just wanted to introduce this notation of lambda w for lambda a core means the block, all the partition, p regular partitions, which have p core lambda after pulling off w. All right, so the more p hooks, the more non-semi-simple the block. All right. So for example, if w is 0, then this block is just a copy of vector spaces. There's one simple, there are no non-trivial extensions. On the other hand, if w is 1, well, it's something more complicated. It's a zigzag algebra for AP minus 1. So for example, for p equals 2, I just get polynomials mod the square of the generator. But for larger primes, I get something a little more complicated. But you'll note here, in both of these cases, there's no dependence on lambda. I get the same answer for all lambdas. And that's maybe not that surprising, right? Like, you know, there's some other copy of K vector space. There's no other category of B if the block is semi-simple. So the sort of maybe slightly surprising thing here is that these guys are all non-semi-simple and exactly the same. And ask, well, does this generalize? Do we always get that the block as a category is completely independent of the core, no matter what the weight is? And of course, I wouldn't ask that question. If that were true, I would have just told you the theorem. So what was conjectured instead, this is one of these theorems that it was a conjecture so long that people often still call it Broué's conjecture, even though it's been a theorem for almost 20 years now. These blocks are not equivalent as categories, but they're derived. If you don't know about derived categories, I apologize. I'll say a little bit more about them later, but the important point is you have to consider complexes of modules in my block. And so I get an equivalence between some categories of complexes, but it has to send a module here to a complex of modules. And in fact, it's defined by I take a module here and I found by a complex of functions, which, assuming there's time, I'll try to explain a little bit about that. And in particular, this complex of functors, well, you know, how am I going to relate two of these blocks? I have to somehow look at the block corresponding to one core and another one to try to get some connection. Yes. Oh, yes.
I missed this. What math?
Any other P core?
Oh, okay. So you just need the same way.
Yes. So yes, sorry, I should have said for all.
And maybe a comment is the reason that we call it conjecture is because it's a conjecture for almost all groups.
Well, yes, that's true. There is a more general conjecture that and if you have two blocks that have an abelian defect group, they'll be derived equivalent. That's fair, right? There is a Broué's conjecture which has not been proven, but this is the theorem. So we can keep calling that Broué's conjecture and call this the Chuang-Rouquier theorem. All right. Any other comments? Okay, the way they find these equivalences is they look at the Weil group of SLP hat. So as I said, the blocks correspond to weight spaces for SLP hat because the number of boxes of a given content tells me which roots I subtract to get my weight space. So when I act with the Weil group, what's going to happen is I will change the core and I will keep the p weight the same. The p weight, if you're thinking in terms of SLP hat, removing a p hook is adding delta to the weight, and adding delta commutes with the action of everything in the affine Weil group. And in fact, you can check blocks of the symmetric group of given p weight form a single order. So for every core, there's an element of the affine Weil group that sends it to any other core. So there's a chain of reflections I can do in the affine Weil group that sends me from one core to the other. And just in the interest of time, kind of throwing this abacus stuff up, mainly for those who know it, but this is kind of a common way of describing partitions, which is you look at the outer edge of the partition, continuing infinitely upward. On one side, indicating this way, on the other side, I'm doing everything in French notation. I apologize to those for English. And I record this by, for every downward edge, I put a dot on my abacus reading like this. And for every sideways edge, I leave an empty spot. So the empty partition is all downward and then all sideways. So I have all dots and then all empty. And then every time I add a box, I move a bead one step to the right. And if I move off the end, I move over a bit down. So for example, here, right, what happened is when I added this box, I moved the dot over here. When I added this box, I moved it here. When I added this box, I moved it here. And then when I added this box, I moved it here.
Number of runners is p.
The number of runners is p, yes. So I'm identifying z by with 1 dot 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 up to p times z via the map that sends ak to a to the minus k. So one of the reasons this abacus stuff is very nice is removing a p hook is pushing a dot up, right? So which runner I moved from is telling me what the content of my box was. So removing a p hook is exactly pushing something up. So this is a 3-core, and I can see that from the abacus because I can't push a bead up. So the p core is just how many dots are there on each runner, and the p weight is how many times do we have to push up to get our runner completely compressed. These are a few examples, right? So this guy is not a 2-core. How did I get this abacus picture? I had a dot here when it was empty, and I went bang, bang. I think I did this right. Hopefully I didn't make a mistake. Maybe it's, oh no, sorry. That was a mistake. I think there might be some mistakes in these abaci. Unfortunately, have limited time to fix them. Yeah, okay, good. Sorry. These guys are not in the same block, so they don't have the same number of runners on number of beads on each runner, which is good. So this guy is not a 2-core because I can push a bead up. This guy is a 2-core because I can't. Here, I have one block for f of S3, and both of the three regular partitions have the ability to push a bead up, and I get the empty diagram. And here, if I look at F5, or more generally a bigger prime, all of my block, I'll get all separate blocks that correspond to different 5 cores. All right.
So the bead that you move is determined by the row of the box, is that right?
The bead you move is determined by the content of the box. So like here, right, I added a box of content 0 and I moved a bead around. Then I added one of content 1 and I moved here. Then I added one of content 2 and I moved here. Whereas here, I added a box of content 0, one of content 1, and then one of content minus
1. If you have 2 beads in the same runner, 2 choices for which one to move.
1. Well, they'll correspond to different addable boxes.
Right, so how do you know which one to move?
Well, which box do I want to add? Are you asking about the Categorical operator?
I mean, you're saying as I add boxes, I move beads over, but how do you know which bead to move?
Which one are you adding up?
Okay, so for example, here, I have 2 beads on this runner I can move right. That corresponds to having 2 addable boxes of content 1, and those 2 addable boxes are here.
Right, so how does the box correspond with the bead?
So I mean, it's this rule. But somehow the point is reading the beads like this tells me where I should have downward parts of the edge and sideways parts of the edge, right? So this bead corresponds to this, to this sideways part of the edge, and this bead corresponds to this sideways part of the edge. And the fact that I can move them right means that there's an addable box here, and there's an addable box here, both of content. Okay, why am I bothering you with this? It's because actually there's a really nice way of thinking about the file group action in terms of Abaca. So what the file group does is it swaps the runners. So if I act by SI, I'm having my I is not equal to A issue again. But if I have A not equal to 0, I swap 2 consecutive runners when I act. And if I have S0, then I swap the last runner and the first one, but I swap them with a shift. I take this guy and move it over here and I shift it down. I take this guy and move it over here and I shift it up. So that's how the affine file group acts on P cores. If I start with a abacus diagram where all of the runners are solid, I act on that by the affine file group via this rule, and that will send me to the diagram for a different P. And if you want to write this in terms of coordinates, we use Ti for the number of kind of extra beads or missing beads on the runner. And how this acts is it swaps TIs, and then S0 swaps the TIs with a translation. So this is the usual action of the affine file group on, let's say, R to the P, C to the P, whatever you want. So you'll note here, this is the semi-direct product of the finite file group, the permutation group, and translations by the root lattice, which is the integer translations where all the integers are. Because I have +1 and -1 here, I can never get something with the integers constant speed. All right. Are there any questions? So I'm sorry to those of you who haven't thought about abacuses before, but this is such a nice picture. It's sort of hard to describe what's going on without explaining it. All right, so how are we going to think about this file group action? Well, luckily, each generator of the viol group comes from one copy of sl2. So each generator of the viol group is going to correspond to one sl2. And in the interest of time, I don't want to get super deep into this, but I also love this proof, so it hurts me to skip over it. The key point with all of these things is the thing I mentioned yesterday about the sl2 action always being built from copies of this original representation we defined, L of N. And let me just give you kind of the brief synopsis of how to see this. So you start with a simple that's killed by En. And, you know, since this is true for the symmetric group, any simple, the endomorphisms of that simple will be the base. You'd have to do something a tiny bit more complicated if you're in a non-algebraically closed situation where that doesn't happen, but this is always the case for us. So a really beautiful kind of little analysis you can do is you look at Hom from Fa of L to Fa of L. I use the adjunction of Hom from L to Ea Fa of L. By the SL2 relations, I know that this guy on the right-hand side is K copies of L. So this Hom space is K copies of this Hom space plus K copies of the base field. So this tells me that I have Y in this Hom space, it's nilpotent, so its K power has to be 0. So it would be really nice if these powers of K of Y were linearly independent, because then I would know that they span this Hom space, and I would know that this Hom space was actually polynomials in Y mod Y to the K. Sorry, dependent when I mean independent. And the way we check this, so I'm not, you know, I'm going to skip a lot of details, but this trick is so important that I really want to emphasize it. The nil-hack algebra, that's always what saves us. If I, instead of taking just one copy of F, I took the K power of F, and I took Hom of that to the K power of F applied to F. Well, what would happen? I know that there's a Hom from the nil-hack algebra to this Hom space. On the other hand, using my SL2 relations, the dimension of this Hom space is K factorial squared. So I have this nil-hack algebra, which I know is a matrix algebra, of size K factorial. And I know that I have a quotient of it, which has dimension K factorial squared. So it must be that I am taking the nil-hack algebra, I'm modding out my maximal ideal, and I'm getting an isomorphism to this Hom space. That's the only way I can have such a thing. Right? It's not 0 because it sends the identity to the identity. And this guy already has dimension so small that the only way it could show up by modding out by a maximal ideal in anything. And because Y is nilpotent, there's only one maximal ideal it could be. It has to be the positive degree symmetric functions. So this has to induce an isomorphism from this Hom space to the cyclotomic quotient of the nil-hack algebra with order K, which is a matrix algebra over the field. That's just the only quotient of the nil-hack algebra that has the right properties. And once you know this, everything falls into place, because these powers are linearly independent as elements of this cyclotomic quotient. So they must have been linearly independent in Fa applied to M. So I just wanted to kind of emphasize this trick. It's hidden in the bowels of a proof in Chuang-Rouquier, but it's the thing that makes everything work. All right. And maybe I'll just note here, we had these kind of discussions earlier about the fact that there are like different versions of the definition of SL2 categorification. This is the analysis you need to check that those are all. That I can take the definition I gave and turn it into the version where I require these maps to be isomorphisms, because I can check that that happens on L of L, and that kind of makes everything work. And if you want, you can do a bit more work, go read John's paper about this, and it will tell you that you can actually rewrite everything in a much more explicit way. Add in an adjunction going the other way, and then get these nice relations involving the crossing to the bijunction. Somehow there's a bunch of pictures here that only make sense once you define the bijunction. But they're actually implicit in these relations. And John Brendan was the one with sort of the audacity to think that you could possibly prove that. And also maybe the only one who could write out the teaks for it. All right. Let me just skip this part. The important thing I want is that when I start with this highest weight guy, I now get my chain of Kashiwara operators. So I can apply F to it, I can apply the divided power of F to it. That always ends up again with one of these guys with a unique simple quotient. Right. If I start with a highest weight guy, then applying any divided power of F will get me something with a unique simple sub and a unique simple quotient. And there's one really important special case of this, which is if I go all the way down to the end of the chain and I apply the kth divided power, this guy is already simple. So all the other guys, there's going to be some weird composition series. But if I go all the way down to the other end of the chain, I just get another simple. But this is, no, it's not written. That wasn't quite the statement it was made. Okay, so important corollary. If my K is maximal such that my weight space is non-zero. So if I look at K plus R for any positive R and I get 0, then actually applying these divided powers are equivalences of categories. They're equivalences of abelian categories. So this is sort of useful already. In KSM, these are exactly the Morita equivalences that we block that were for Webster's. Okay, well that's great. But what if I have something non-trivial in CK plus 1? So for the sake of this argument, assume that only CK plus 1 is non-zero, but I have a simple there. So if CK plus 2 is 0, that means that E of this L is 0. But then FL gives me an object in CK that where this trying to use this divided power as an isomorphism just doesn't work. I apply the divided power to this guy, I get K copies of the K plus first divided power applied to it. So I'm starting with an indecomposable thing, or something that's certainly, a simple thing, and I'm hitting it with a functor and I'm getting something decomposable. So obviously that's not an equivalence. It only works in this case. So how do we fix this? Right? What I want is to just send FL to the K plus first divided power of an L. Because that's what I sort of saw in this chain. This whole thing is kind of symmetric. Well, it turns out there is a way to do this. Because EF of L is K plus 1 copies of L, that's the sl2 relations again. There's actually a short exact sequence where if I take Fk plus 1, the divided power, times E times FL, and take the natural map of that, any surjective map of that, from to F, the K divided power applied to FL, the kernel will be this guy I wanted, the K plus first divided power. So I have this complex, right? F to the K and E F to the K plus 1. And somehow this gets the things I wanted, but it gets them in a funny way. So if I apply this to a module where E is 0, I get that the co-kernel of this map is the thing I want. It's fk to the n. Sorry, and there's a k plus 1 missing here. And so that's the co-kernel if I apply it to something that's killed by E. On the other hand, if I apply it to something that's in the image of F, I get the right thing, but is the kernel of this map instead of the co-kernel. So somehow this complex is doing the right things, but it's kind of mixing things up. If I think about this as a complex, right, the co-kernel is the 0 cohomology, and the kernel is the -1st cohomology. Getting sort of the right thing, but somehow for different objects, it's showing up in different degrees in the cohomology. So assuming we're in this situation where we're almost at the top, not quite, what have we found? So I have a complex of functors going from this guy to this guy. So I can't apply that to modules and get another module, but I can apply it to complexes and get another complex. So it gives me a functor from complexes of objects at C, to complexes of objects at C minus K. All right. So this is the formula of the complex. I take the total complex. Of course, I'm realizing I'm running pretty short on time, but that's okay. Well, that's nice. I don't really want to think about all complexes because there are lots of boring and no cohomology. So I want to take the quotient by the category of complexes with no cohomology. And that's what's called the derived category. So the fact that this functor is going to send exact complexes to exact complexes, because it's a complex of exact functors, means that it sends acyclic complexes to acyclic complexes, and it induces a functor on derived categories from Ck to C minus K. I should maybe emphasize, while this is a special case of the construction of Chuang-Rouquier, this was really observed by Ricard. So in this case, where I take the guy one below the highest weight, this is an equivalence of categories on the level of derived categories. But it mixes things up, doesn't give me an equivalence of the abelian categories. All right. And actually, the same principle applies if I go further and further from the highest weight, but I need more and more terms. So if I get something non-zero by doing E twice, I have to add in this term fk plus 2, E2. If I can get something by applying E 3 times, then I get E3, fk plus 3, etc. And I'm not telling you what the maps in this complex are, but they're ones you can build from these crossings and caps. And you can check that it's a complex using these relations.
And how did you observe it on that slide? How did you observe that what exact sequence exists?
I mean, it's a little bit of luck, but somehow, if I think about what happens on an object of the form FL, then applying the k divided power gives me k plus 1 copies of it, and applying this guy instead gives me k copies of it. I might have this the wrong way around. I'm a little worried, but oh yeah, sorry. This gives me k copies of it. This gives me k plus 1 copies of it. So there's a map where I can write 1 copy of it as the kernel. That's all I'm using. I mean, you know, obviously, there's a certain amount of you just write this down and it works. But if you want to kind of justify, this is sort of the most simple case where you can see, okay, this is kind of why this would be the right thing to do. All right, so here, Chuang-Rouquier, this is a derived equivalence. And so it gives me a derived equivalence between the blocks, where I have one core, and then another core where I've swapped the runners. Now, this seems very abstract, and I don't have much time to fix that, but I'll do what I can. So what it says is sort of these categories are equally complicated. And as we saw, what happens there, it matches simples using this Categorical operator. And the way it matches them is sort of roughly a shift. So, you can bother Oded about this after I'm gone. It's a perverse equivalence. And you can actually describe reasonably well the sort of filtration that it's perverse with respect to. So I can look at, any sl2 categorification, and it has a filtration by subcategories. So I'm fixing one block. I look at the filtration by guys that are killed by applying e to the r plus 1. That's a perfectly fine subcategory. And that filters my block, filters my weight space category. And this is for k positive. There's an analogous thing for k negative where you apply f's instead of e's. And this theta, exactly what it does is it induces an equivalence of abelian categories on this quotient, but with a shift. So like we saw here, in this case, where on the subcategory things that were killed by E, it showed up in zero homology, whereas if I mod out and forget about all the things that are killed by E, it shows up in the minus first homology. And this is a consistent pattern. So this is what's meant by perverse. So the reason I say this mainly is to emphasize the number of layers in this filtration, which is to say the number of different lengths of sl2 strings going through my block tells me how much this equivalence fails to be an equivalence of the abelian categories. Right? If I'm in the top weight space, all the blocks have the same length. They all have length n. And this guy is an equivalence of abelian categories. Whereas if I have a bunch of strings of different lengths, then I won't be getting an equivalence of abelian categories. I'll be getting something where things move by different amounts for different symbols, depending on the length of the sl2 string they're on under the Categorical operators. All right, I'm running pretty low on time. This is just restating the crystal rule I said before, but in terms of Bapat. So if I have a level where there are two beads, I look at two consecutive runners, that corresponds to fixing attention on one Categorical operator. If there are two beads or no beads, then that's no addable box and no removable box. If I have a pair of this form, where it's northeast, southwest, that's a canceling pair of parentheses in my original rule. So I get rid of those, and the remaining things all have the form have a bunch of dots. Then I have a bunch of dots on the other runner. And again, the Categorical operator is pushed to the top dot here and the bottom dot. All right. Yeah, cores are boring. Let's not worry about that. What usually happens is the higher the p weight is, the more p hooks we have, the kind of more layers in this filtration. I wanted to illustrate this in an actual particular case. So I'm going to take p equals 2, because that's kind of easiest to deal with. I'm going to take weight 2. In this case, there are two objects in this block that correspond to these partitions, and thus these Bapat. And I want to look at what happens when I apply S0. So the annoying thing is I have to apply that rule, but with a shift. So I drew the pictures down here where you can see, so I've swapped the runners and shifted them so you can actually see how to compare things. And when I cancel the bad pairs, this guy is on a root string of length 2. Right, so I can see the length of the root string by how many uncanceled things do I have left. So here on this guy, I have one bead I can move. Whereas here on this guy, I have 2 beads on it. All right. So this is telling me I don't get an equivalence of abelian categories. We go back to, if we go back to this picture, right? This is exactly focusing attention on this root string. This root string. And exactly what we see here is we have a string with 3 steps, so 4 partitions, and one with 2 partitions in it. It's when you see that thing with different lengths that you don't get an equivalence of abelian categories. So one of these symbols doesn't get shifted, and one of them does. Now it's worth noting, once I've done that, I can then say, oh, well, what happens if I go out for bigger and bigger p-cores? Which I just always do in this p equals 2 case. I apply 0, I apply 1, I apply 0, I apply 1. So now I'm here in this block with 2 core given by buttons. And I'm going to go to the guy with 2 core given by staircase. And if I apply the Categorical rule, operator rule now, well, I don't have any spots on my runners where there's a feed to the right of an empty spot. So there's no possibility of cancellations in my Categorical operator. Everything is on as long a string as possible. In fact, these guys are highest weight objects for E1. Right? Yeah, because I can't move any beads from this runner to this runner, which is what E1 would do. So when I do the Categorical operator for that one, I just move all the beads I can, just swap the runners. So this guy is an equivalence of abelian categories because all the root strings have the same length. I'm actually in the highest weight space for an sl2 categorification. So if you think about these blocks in p equals 2 with weight 1, it turns out there are only 2 abelian categories. There's the principal block for S4, and then there's all the other 2 cores. All the other 2 cores have equivalent categories. And the basic idea is, as you go further out, the gaps between the number of dots on the runners grow. And if you're going around in your affine Weil group, the gaps have to grow. That's what you saw here. Now there are like many more beads on this runner than on this one. Go further out, that's going to get more and more and more extreme. And well, once that gap gets big enough, if you fix the weight, if you have a block with small weight, there's no way that you can be in the middle of a root string. But these always become equivalences of abelian categories after a few steps where they're not. Are any questions?
I think I'm reading a little ahead. I'm trying to understand the definition of rock.
Oh, okay. Yeah, well, I don't have time to talk about that. Yeah, let me just say there's a bunch of stuff in the notes that I'm now going to run past extremely quickly. So what this tells us is, it's not like we're getting different abelian categories for every people. Actually, lots of p-cores have equivalent categories. And there's kind of a biggest class of them, which is called the RoCK class. So this is basically just saying that there's a very big gap between the number of beads on each runner. If I look at any pair of runners, there's a big gap between the number, and for some subtle reason, I need the difference to be W sometimes and W minus 1 sometimes.
Is it possible to say what that is in terms of lambda and W? No, in terms of evidence?
Probably. I would need to think about it, and I don't have time. So you can show that all of these blocks are equivalent to the abelian categories. I wanted to kind of get out to this picture. So, right, when we were sort of moving around and comparing different blocks, we were basically doing a walk in the affine Weil group. And there's actually a nice way to think about these walks, which is, I think I have this here. If I write my W, if I write my W as SIN up through SI1, then actually it's helpful to look at starting with the fundamental alcove and then applying these kind of reflections. Yeah, I'm sort of doing a bad job explaining it. I mean, the important thing is I ultimately want to look at W inverse times the fundamental alcove. And I want to path out to that guy where each step crosses one hyperplane. And you do have to do a slightly weird thing to do this.
Where are we talking about alpha suddenly? I lost the question.
Okay. Yeah, well, I skipped a lot of stuff. Okay, so let me emphasize this picture. So there's a nice way of matching up P cores with alcoves.
This picture
And
P equals 2.
this is for P equals 3, right? Because it's going to be alcoves for SLP hat. So P equals 2 is aligned over. Right, for P equals 2, right? All the P cores are staircases, and it's just you add one more set of stairs. And the rule is for every P core, there's a W that sends you to the empty P core, and you apply the inverse to that. And that allows you to think of a chain of applying these reflections. So for example, here, this corresponds to taking the empty P core and applying this reduced expression, but in the opposite order to it. There's this kind of annoying thing about taking inverses. But the reason I'm doing this is if I look at the alcove for S0 and then I apply to S1 to it, would jump really far across the diagram. So instead, I'm adding my reflections onto the back. And that always moves me across one hyperplane. So for example, this guy, I can think of this chain going from the empty partition out to, what is it? This guy as a walk on this alcove. And the thing I wanted to get to, I'm out of time, so I should probably just quit, is there's actually a nice rule for which there are a finite number of hyperplanes where you don't get an equivalence of abelian categories when you cross them. And it only depends on which hyperplane you're crossing, not on where you're crossing it. So in the case of the symmetric group, it's the hyperplanes that are defined by the finite roots take values between W minus 1 and minus 1. So the absolute value is less than or equal to W minus 1. So here, this is W equals 3. Add hyperplanes where the finite positive roots of SL3, sorry, take on the values 0, 1, and 2. And the categories for 2 P cores are equivalent to abelian categories if under this picture, they're in the same chamber. So every one of these alcoves corresponds to a P core, and drawing these hyperplanes tells you which P cores. And every time there's an adjacency of 2 P cores across a hyperplane, that's telling you a simple reflection that sends the block for one to the other one. If there's no hyperplane here, so here, the Chuang-Rouquier equivalence is T exact, it's the equivalence of abelian categories. Whereas if I go from here to here, it's not. And this is just sort of checking when you have more than one layer in this equivalence.
This is if I don't get, right?
You have to be, it's true that this is if and only if the functor theta I is t exact. You have to watch out a little bit for when it's the shift of something t exact, because that can happen, and you need to delete some of these hyperplanes to account for that. And I should emphasize that, of course, it doesn't account for the possibility that blocks are equivalent as abelian categories, but in some other way.
Does not happen.
Yes. You can tensor with the sign. There's an equivalence between categories, which I'm pretty sure is not. I don't know, Chris and I were bullshitting at the bar about whether there are any other ones. Maybe there are, maybe there aren't. I don't think we know any examples, but it's hard to rule out. All right. And I think I'm out of time. So I'll just say, we'll talk more about this at the conference.